because now it's 11:15, and so on our schedule is the next talk. I hope I pronounced the name correctly. It's Konstantin Rjutin, and he will speak about the recovery of rich functions.
Thank you. I'd like to thank the organizers, and I try to open my presentation. Is it okay? Do you see it?
Looks good.
Yes.
Everything seems good. So the title of the talk is The Recovery of Rich Functions, and I think that it can be regarded as some supplementary talk to the one given by Jan Wiberau. It was, I think, on the first day of the conference. So here we will discuss more or less the same or a similar problem, and so let's do it. So I will talk about the joint research with Tatiana Zaitseva and Yuri Malykhin. Tatiana Zaitseva is a student in our laboratory of higher dimensional approximation and applications, and Yuri Malykhin is a researcher in this laboratory. So, and maybe some of them can answer some questions at the end if there will be some questions. So I start. We consider rich functions on the ball, on the unit ball in n dimensions. So this rich function, what is this rich functions? It's a function which of one variable phi, which depends on the scalar product of a fixed vector a from Rn with x. So it's we can suppose that this vector a is normalized, so its norm is its Euclidean norm is 1, and so this function phi is a function from the segment -1, 1 to R. So we want to recover this function f from n imperfect samples. So they ask for some values of our function f, but they receive the result with some possible errors. So the problem is not so easy, as we can easily see that for any choice of points x1 to xn from the unit ball, when the number is not very large, namely its log is or small of n, we can find a unit vector with a very small scalar product with all these points xj. And so when they take the samples of our function f, we obtain only some information on its behavior in a small neighborhood of 0. And so it is difficult to distinguish between this function and the identically 0 one. Even if we allow ourselves to consider adaptive algorithm, that means that the choice of each point can depend on the choice of the previous points. Even in this situation, it is impossible to recover, to organize an algorithm that recovers all functions from reasonable classes if the number of evaluations of the function evaluations is not exponential. So, and here I give some ideas how to see it. So let's go to the next slide. So this problem is within the recovery of function theory. First studies were done, I think, in 1950s. But the main focus for the first period of its of the development of this theory was on the best possible recovery method for smooth functions. And nowadays there is a very interesting line of research within the information-based complexity theory, and one of the main questions is how the number of function evaluations depend on the dimension of the space. So we want to recover some unknown function from a given class with a given accuracy, and we ask ourselves how many point evaluations do we need for it. So if its dependence on the dimension is exponential, then we call this situation the curse of dimensionality. Results on the existence of recovery algorithms with small number of evaluations, say polynomially, depending on the dimension or something like that, or contrary to that any algorithm requires a large exponential number of evaluations, are studied within this just mentioned information-based complexity theory. So at the end of my talk, there is some references, and so I see. So let us consider the following situation. Consider the class of functions fd, C infinity functions on the unit cube, such that all possible partial derivatives in the L infinity norm are less or equal to 1. And we try to consider all possible reasonable recovery methods of the form written on this slide. First of all, we take some evaluations. That means some mapping from this class fd to Rn. And later we take some recovery operator, some mapping from Rn to L infinity over the d-dimensional cube. And a very important and very seminal result in this direction by Novak and Wozniakowski was that this measure of then they try to measure the possibility of such a recovery of a good recovery operator, then we cannot do better than a constant accuracy. So this E of nt equals to 1 when the number of point evaluations or some other kind of evaluations does not exceed the exponential in the dimension of the space number of evaluations. So in order to recover accurately, one needs exponentially many function evaluations. So let's get to our problem on the rich function recovery. We consider I will introduce several classes of rich functions. We will deal with functions on the ball, but for historical reasons, and we'll talk also about functions on the cube. So here we see, and we talk about I think the first result in this direction, the one by Cohen, Dobeshy, Devor, Kerkachyan, and Picard. They consider the recovery in L infinity norm for smooth rich functions on the cube. They assume that this function phi is Hölder of class R or Lipschitz of class R, And additionally, the authors of this paper suppose that the vector A is non-negative. Namely, all the coordinates are non-negative. This condition is very restrictive, but it permits to recover our function f phi at any point in the form written by the formula written on this slide, this formula. And also there were some other conditions that permit to recover our function phi. So it's easy. It's more or less easy to see that this condition is restrictive, and at the very first step we get a huge amount of information. We know that our vector A is situated in some fixed ortant of the n-dimensional space. So the studies were continued by Doyer and Meyer. They dropped the non-negativity condition and replaced weak LP condition by the following one, that they suppose that they have some control on the LP norm of our vector A with p less than 1. And they provided an approximation with accuracy, which I wrote here. And also they proved that without the condition 2, we still have the curse of dimensionality. So they proved also the lower bound for the possibility of recovery. Range functions on the board are considered by Fournazier, Schnass, and Liberal. I think that Jan talked about this paper and the result on Monday, on the first day of the conference. And also they considered a more general situation than we consider not only rich functions, but also the functions of this form, when there is some function phi, and also there is some matrix k to n matrix, and the main condition on the function phi in order to guarantee the recovery is the behavior of this quantity. We consider this integral over the unit sphere, and they prove that if under some restrictions on our vector A for functions phi which are C2, if alpha is this quantity alpha is not close to 0, so they can understand this. One can understand this requirement as that the derivative of phi at 0 is separated from 0. Then the efficient recovery of f is possible. Morally speaking, this number of point evaluations are sufficient in order to achieve the error not greater than omega with high probability. The quantity, this alpha quantity they considered in their paper, can be very small for classes of functions which we are interested in. So here I write some text about this situation. So our class of functions, we consider analytic functions. It contains a function with oscillation more than omega, but this alpha quantity less than this exponent. So if one tries to use the algorithm developed by in this previous paper, then one needs to have a non-polynomial number of point evaluations. Also in the paper by Meyer, Tine Ulrich, and Jan Wiberow, some different approximation characteristics for several classes of rich functions on the ball were estimated. And as a corollary, the formal proof of the curse of dimensionality was given. So also I should mention that a closely related problem in statistics is known as a single index model regression. It deals with the following situation. We take some random vector x and also some random variable y. And we assume that the regression function, this one, is conditional expectation, and has the form f is some one-dimensional function of the scalar product with a fixed vector a. So in our terms, it's just the rich function. So, and we are required to construct a regression AI we want to approximate f from a sample x, y, y, I. But we should stress that we, contrary to this, to the activity from statistics, in our situation, we are not free to choose these points x. They are a random sample from the distribution unknown to us, and also the error is measured in L2 rather than in L infinity. So I should also mention that for classes of analytic functions, the recovery problems were considered from 60s, but the main focus was on the best possible method and such kind of questions. I should mention papers by Haynes, Havinson, Walsh, Micheli, Rivlin, Sipenka, and others. In our paper, we use from the very beginning and even to the practically to the end of the paper, the recent result by Demanet and Townsend, that an analytic function is extrapolated from its noisy evaluations on the grid using least squares fitted algebraic polynomial. And similar results were obtained by Platte, Trefethen, Adcock, Hansen, and Chandrid. So Sergei Vladimirovich Konyagin, I misspelled his name here, suggested to consider the case of analytic rich functions. We consider this kind of rich functions. We take some rectangle in the complex plane of this form, and we suppose that our function phi is bounded by q in this rectangle. It is real valued on the real line, and also it is analytic in this rectangle. And we provide a polynomial recovery algorithm, probabilistic, for this problem. So we consider functions on the unit ball, and this function phi is from p sigma. So here is the main result. Let's fix this notation. N is a number of variables. Sigma is some number from 0 to 1. It measures the dimensions of our rectangle. Q is not less than 1. There are also numbers delta ast and omega ast, and so then there is a probabilistic adaptive algorithm that for any function f from our class, it takes n evaluations with errors not exceeding epsilon. The epsilon and n capital are related to other parameters in this way. And this algorithm outputs an approximation f tilde such that this probability as high probability, we have this approximation. So we should remark that this tilde f is of the form tilde phi of some scalar product with vector tilde a, where this tilde phi is an algebraic polynomial of degree not exceeding some constant which depends only on sigma times the log of q over omega. And the number of operations of our algorithm, it also depends polynomially on these parameters. So we should also mention that our function f is invariant under this change of variables. We can pass from a vector a and function phi to minus a and phi of minus x. So our algorithm recovers either the pair a phi or the pair minus a and phi of minus argument. So here is a corollary in order to better understand the meaning of the parameter or the parameters. There is a polynomial algorithm that makes at most this number of evaluations. So here we see that n times log squared n of an unknown function. We suppose that the errors are not very large, they are small. And with high probability, with overwhelming probability, it outputs an approximation with this power type accuracy in the dimension of the space. So let's proceed to some details of the argument of the algorithm. So here is some notation and some preliminary discussion. We suppose that q is equal to 1, and the small n is supposed to be large. This omega is small. There are several parameters, capital N1, capital N2, and capital N3, and also some small positive reals, omega 1 to omega 3. They can depend on these parameters. So we also fix some function phi and vector a corresponding to our rich function. Our algorithm takes some evaluations of our function f. It makes something with them, and the objects, different kind of objects generated by this algorithm, they are denoted with tiles. So also for any vector gamma, it's very important notation from the unit ball. And we take this number v gamma, it's n1/2 times the scalar product of a and gamma. And also this tilde phi gamma, it denotes some approximation for this function. We will see it in several minutes. So we also fix another important definition. We take two numbers, b small and b capital. In fact, b small is something like 0.01 and b capital is something like 5. Their choice is determined by the properties of the uniform distribution on the sphere. And we call a number typical when its modulus is between these two numbers, b small and b capital. Here also is some notation. And let's go. So the scheme of our algorithm. The first step. So for any vector gamma in the unit ball, we evaluate our function f on the grid. It's a uniform grid in the direction of this vector gamma. We take n, capital N1, large enough, and we compute, or we ask the oracle for the evaluations of our function on this at these points. In this way, we obtain some kind of information about this function phi of v gamma t, on the uniform grid in this segment. And we fit a polynomial of an appropriate degree m to obtain values by least squares. And later they use it to extrapolate this function phi to larger segments. So we rely on the estimates from this paper mentioned before by Demane and Townsend. And this paper with some computations, it gives us that in this way we obtain an approximation with this error on this segment. Then we take the second step, namely we take several directions on the unit sphere, and for each of them we construct these functions phi tilde. For each direction gamma, we construct this approximation, this polynomial, and this approximation phi tilde gamma. As a result, we used this number of function evaluations and obtained a set of polynomials, in fact, algebraic polynomials, this set. So since our choice of these directions was random, our algorithm is probabilistic, and all other constructions and steps of our algorithm, they depend on the properties of these gammas, namely on the condition 13 given below. So at the next step, we have to deal with a very important question. There are two different situations. The first one is when our function phi is close to being a constant, or is simply a constant. It can occur, and we have to somehow distinguish between this situation and the situation when our function behaves nicely at some neighborhood of zero. In order to do it, we try to evaluate the oscillations of our function phi, and this step is very important. We either obtain that it can be approximated by the constant, or that we obtain that its oscillation in the neighborhood of zero is not small. If we have the first situation, then everything finishes here, and we can approximate our function f by its value at zero, and the algorithm stops, and we are done. In the opposite situation, we proceed to the next step. So here is the main part of the argument. So that is so-called embeddings between different functions. The problem is we do not know the values of these quantities v gammas, or these numbers v gamma, but a simple idea helps us to approximate their ratios. They can approximate the ratio of the absolute values for any pair of vectors gamma 1, gamma 2. Namely, from the approximation, it follows that phi tilde 1 is approximately phi tilde 2, but the argument is dilated by some number lambda not less than 1. If this approximate equality holds, then we call it an embedding. And we show that for typical v gamma 1, the corresponding lambda can be found with high accuracy, namely this such an estimate. The next step is the search for a typical v. So we have a certain set of polynomials of these functions phi gamma I, and we analyze this set of polynomials, and we try to somehow understand we try to find some function phi tilde with a corresponding v which is typical. So the goal of the step to find an index such that this variable, this number v, is typical. In order to do it, we consider all possible pairs of these polynomials, and we search for all possible embeddings. We do it on the grid. And so it's the main step. After this is achieved, the recovery of our vector A and after it, the recovery of our function phi on the whole segment is more or less is not easy. It's is not difficult. It's rather easy. And for our estimates, we also use the property of our function f, that is, it's in fact Lipschitz, and its Lipschitz constant depends only on sigma for the whole class of analytic functions which we consider. So here are some details. First of all, some words about this paper by Demonet and Townsend. We evaluate our function f on the uniform grid, and we arrive at the following situation. We have some function psi of z that equals some function phi of u z. U is this scalar product, and we use the results from the paper by Demonet and Townsend, and they considered the following situation. They considered analytic functions in ellipses with foci in plus and minus 1, and the sum of semi-axis rho. So here is some kind of some variation on the result. So we have these estimates. If we are given the values of function psi at this uniform grid with accuracy not exceeding epsilon, and we simply take the polynomial, the least squares polynomial of degree not exceeding m, and this m is behaves like a square root of n number of point evaluations. Then we have stable interpolation and stable extrapolation with these estimates. So when we apply the result, we arrive at this situation. And after some simple changes of variables, we arrive at this function phi tilde gamma. So we do not know. So we arrive at the following problem. We have to recover an unknown function phi from the following information. There are numbers vi and functions phi of this form. We do not know these numbers, and also we do not know these functions. But we do know the approximations phi tilde y I to these functions. And we want to somehow understand from this information, to find from this information the function phi and this vi. We do not know the numbers vi, but we know that vi is a sample, in fact, a sample from a random variable with a known distribution. So here is the statistical or probabilistic part of the proof. So this, in fact, this numbers vi is a sample from the random variable. We take the uniformly distributed vector on the unit sphere, and we take its first coordinate. We normalize it in this way, and we consider the distribution function of its modulus, and also the empirical distribution function of the sequence. And we use, maybe there are some questions. Do you hear me?
Yes, I hear you.
Okay, but I read something in the chat and it misguided me. So they consider the situation. They use the following facts: that it's the distribution functions of Fn is close to the distribution of the modulus of the standard normal variable, and also they use the Dvoretsky-Kiefer-Wolfowitz inequality. And from these two rather well-known facts, we obtain we get some control on this. They get some control on these numbers vi. So they more or less need this kind of facts, that the number of indexes I such that the absolute value of vi is between 1/2 and 2 is greater than 1/2, and also we can control this kind of information on the numbers vi. So here are some additional details, but I think I'm approaching the limit of my time. Maybe we will skip them. So here I describe, I give more details, how to evaluate this oscillation of our function near zero. Also, they needed this simple lemma for analytic functions. It tells us that if we take any function of our class H sigma 1, so we control our function on the rectangle. Its dimensions are controlled by this number sigma, this number sigma, and we know, and we are interested in oscillations of our function c over the segment of length 2 tau. Then there is such a relation. So maybe I'll skip also this part. So here are some formal definitions concerning this what we call general embedding theory. So the embeddings between two functions, or maybe it's better to say between the graphs of two functions. So here is this situation. We have some functions j, y, and some approximations for them, and we know that these functions are in fact they are in fact parameterized by a single function j, but the arguments are different. They are dilated by vi for each index. And so here is the main and the most important definition for our work. So we say that some function h1 embeds into function h2 with coefficient lambda and accuracy delta when we have this inequality. And also they can define the embedding when we replace the maximum over the segment minus 1, 1 with the maximum over the grid of step nu. So when we work with our algorithm, in fact, it deals with grids, not with functions on the segment, but with some information on different grids. So and also the main point why everything works smoothly is the following simple idea. So it is written here. They have this simple fact: if h is continuous, and we know that in fact this function h satisfies this equation, h of theta s is identically equals h of s for some fixed theta in 0, 1, then in fact it's a constant. But in our situation, we need some quantitative result in this direction, and it is written here. So for Lipschitz functions, we have this very important lemma. It's an easy one, but important. And here is the main the lemma which we use in our algorithm. It describes how this embeddings on the grids and the embedding on the whole segment are related to each other. So maybe I will skip this. It's rather technical. So here is the slide about the choice of parameters that appear in our algorithm. And here is the what is called the some kind of implementation and numerical results. The student from our laboratory, Tatiana Zaitseva, who's our co-author, and also Yuri Malikhin, they conducted these numerical experiments. They considered this class of functions. It's some algebraic, it's a mix of algebraic and trigonometric polynomials. And in this situation, they used some simple modification of the algorithm and tried to recover these different functions from this class. Here are some details of what changes in this situation. They used L2 approximation in this situation in order to find this constant mu, that we call the embedding constant. And because everything is polynomial and the metric is a very nice one, it's L2. It's easier to implement it numerically, and so they tried several. They made several experiments. This is one of them. The number of variables is equal to 50. The accuracy is this one. So here are some numbers related to the number of evaluations. And these two numbers, K1 capital and K2 capital, they are needed, they parameterize the complexity of this family of functions. Here is an example of the function that they considered. You see that it's very, very close to 0 at some rather large neighborhood of 0. And here are the numerical results of this implementation of the algorithm. And also this parameter alpha is given for this situation. So this is the paper by Demanet and Townsend about stable extrapolation of analytic functions, and also some papers mentioned in this talk. So I think I'm done.
Okay, so thank you very much for the very interesting talk. Are there questions? Okay, so there seems to be no question. Maybe I have one. Do you have certain applications in mind when you implemented this? Is there some motivation from physical?
Hope that someday in the future,
okay,
maybe we'll find some real applications. But nowadays it's more or less some experiments.
And I also, so I'm not so familiar, not very familiar with this topic, but I know that there are some generalizations. For example, that the model setting is generalized in a way that a function is maybe a sum of two rich functions.
Yes. It's very interesting, but at this time they do not know how to deal with this situation.
Okay.
I think that Jan Wieberau, he talked about this problem, and maybe he'll describe his method. And this, we have this question in mind. We plan to think about it.
Okay.
But for the time being, it's the only one rich function.
Okay, it's the first step.
Yes.
Okay, so if there are no
question?
Yes. Yeah.
Maybe I missed this point, but there is another generalization in different direction where you consider, instead of this vector, this matrix inside the function.
Yes. But I think that technically it's more or less of the same order of difficulty as the question mentioned by Martin Schaffer, yes?
Schäfer.
Schaffer.
Schäfer. So.
Okay.
Because I remember when we did this reconstruction of rich functions with a vector and a profile, that actually this generalization was not so straightforward. So it is an additional difficulty.
Certainly.
So we dealt with entropy numbers and coverings of the domain and stuff. And
no, every step here is difficult. So it's definitely not. It's more difficult. Certainly, it's another problem.
Okay, thanks.
But I think that the sum of 2 or 3 or several rich functions, it's more or less of the same level of difficulty as the problem you mentioned, Chess. So it's a challenge.
Okay, so if there are no more questions, then we thank you again for the nice talk. And the next talk starts in 10 minutes.